So let's begin by starting a new text document, and here you can first of all include a library that we often do, which is this one, and then you save it preferably at a known location like the desktop, and you name it something like lab3 um, demo.c, and then you go and start the main function where all your code is going to stay and is going to be run by the operating system. And right, so first of all, I'm going to try to make you uh, you know understand a little more about what variables are, and probably here you're going to learn about variables in much more detail as whatever you already know of variables, if you haven't come across this discussion in the way that I'm doing right now, right? So yeah, so for example, if I define a variable x like this, uh, what do we mean by declaring a variable? So we have what we've just done is that we have declared a variable of type integer uh, and name x, right? So essentially it is going to just go into the memory, and it is going to uh, find a free space inside the space of your program. So for example, this is my program, and I'm assuming that the name of this program is lab the name of this program is lab3 demo, right? And there are various locations inside this address. We also call it the address space. So let me actually, after I am done drawing these divisions, I'm going to you know write that down as well. So for example, this is the you can say address space, or maybe let me call it memory over here, and let me call it over here address space of lab3 demo. So this is the address space of the program called lab3 demo. So whenever the operating system comes across an instruction that looks something like this, which is obviously the operating system will not be receiving the C code, it will be receiving the binary code for the equivalent code for this line. Whenever the operating system receives that and runs that, it is going to go into the address space of your program, which is this address space, and it is going to find a free space wherever it can find a free space, and it is going to dedicate or reserve that space for the variable that we have just declared. So for example, I am declaring the operating system decides that this is the space for which this is all the space where variable x is going to reside. So variable x is going to have two parts. The first part is the what we call the data part, and the second part of this variable is what we call the address part, right? So these are the two parts that every variable consists of, and this is not different by any means, this variable x, and it also has two parts, the address part and the data part. And let me show you, and by the way, the data part is also called the value part. So let me actually use the other name because the value word is, I think, more frequently used, so I'm just going to call it the value part. So this is the part where you store the value or the data for this variable, and then it is also going to have an address. Why is an address used? Can anyone tell me why address is used? Since the variable has occupied a space in memory, and we need to refer or try to get to the value of that variable, we need to have that variable needs to have an address. So that's why every location inside memory has an address, right? This one has an address, this one has an address. Normally the addresses are very simple and they're sequential. The more probably in the computer system architecture, the simplest part I always say is the memory, because the memory simply goes on in sequential numbers. The addresses start from 0, they go on incrementing to 1 to 2 to 3 and so on. The simplest part, and every address has some kind of value in front of written in front of it, right? So yeah, so you guys know what the address is and what address is necessary for. So let me demonstrate to you guys what the address, how we can see the difference between address and value. So first I'm going to use this line and assign the value of 45,700 to the variable x, and now I'm going to use printf, and I'm going to type in the value of x is, and I'm going to use the format specifier called %d. Then I'm going to return new line, and then I'm going to write the name of x. So just by writing the name x, what am I saying? I am passing the value of x to this function which is called printf. So I am just by writing the name of variable x, I am passing the value of x to this function called printf. And the objective of printf is to receive some data and then display that data on the screen. This is what printf does, right? Right? So printf is receiving the value of the variable x because I've simply written its name, and it is receiving this data, and it is going to display this data on the screen. This is all it is going to do. So let me first remain to this part only, and show you the value of so I'm going to start maybe a new terminal, and let's use GCC. Let's first try to find our file. So this, it is not here, so I look for it. So here I can find my file, lab3 demo.c. Now I'm going to run the compile command, which is lab3 demo.c minus o lab3 demo, right? And hopefully it compiles. So there is no warning or error message. It means it has compiled successfully. I'm going to run it by typing ./lab3 demo. It is going to run, and here you can see that it has displayed the value of x, which is 45,700. Although I did not mention 45,700 inside this printf command, I only mentioned the name of the variable. So what did the printf command do? It actually went to this value part of this variable x just by reading its name, and it read over here it was written 45,700. It displayed it on the screen. So this is what happened. Now let me show you another cool fact about the variable x. So the address of x is, I'm going to write some things which you may not immediately understand, but I'm going to explain a little. So actually, let me get rid of this for now. So if I write the value of x, if I want to display the value of x, I simply write its name. But if I write an ampersand sign in front or in start of the variable x, it is going to retrieve or read the value of the address of variable x from memory, and it is going to send that address to this function called printf, and that printf is eventually going to display that address on the screen. That's why I've written over here address of x is, and by the way, the format specifier for address of operator is %ld, and the ampersand sign, as I just told you. So I'm going to write over here ampersand is the address of operator, right? So this is what the ampersand operator does. It takes the name of the variable, it goes to the variable in the memory, and it reads its address, and it displays the value of the, or reads the value of the address. That's it. That is all this ampersand sign does. So this is us who has written this inside the printf function. So eventually the %x value is going to be passed to the printf function, and then the printf function is going to do whatever we expect it to do. So let's go on and try and do that. So it says that it is not going to accept the this thing without what we call typecasting. Typecasting is a method which simply forces the type of a variable to an expected type. So the example for that, in my personal opinion, a very good example not is when you use the spreadsheet software like Microsoft Excel. So you because some people may be familiar with this, some may not even be familiar with this, so I cannot really do anything about those who really don't want to be involved with tech, IT or tech things. So for example, each of these cells are like variables, you must know, in a spreadsheet. For example, the name of this variable is G5, and you can actually specify the type of these variables. Do you know from where? From a thing called format specifier. These things: no specific format, number format, currency format, accounting format, short date, long date, time, etc., etc., right? These are all format, or these are, in our terms, these are variable types. So you immediately see, for example, if I type in 45 and press enter, it immediately right aligns this text. And if I type ABC and press enter, it keeps it in left alignment. So automatically it has changed the value of ABC to text type, and automatically changed the type of 45 to number type. But what if I use the value of this in a formula, like I want to add 5 to this? It has added the value of 5 to 45. What if I wanted to add a value of 5 to this thing? It is going to give me an error because it did not find a number over here. What if I wanted to add a value of 1050 and we wanted to add 5 to this, but instead of saving it as a number, I have saved it as a text. And then I run the same formula on it like this. It still performs the formula. It doesn't give me an error, even though I forced the cell that contained the value 1050 1050 to have a type of text which is a string type. So what essentially happened over here? Typecasting happened. It forced it. The Excel software realized that there, inside the text, there is only numbers written. So what I need to do is automatically convert the text type to number type and then display the value. So therefore it did not give any error in the formula which I have written over here. So this is called typecasting, playing with different types and forcing a type to another type if the expected type is different than. So %x has a system defined type of address, but it looks very similar, and by the way, it is exactly the same as a number. So we are forcing it to become a number using this thing. This is called typecasting. Hexadecimal is just a representation, right? Hexadecimal is how we represent numbers. So for example, you have a roll number. For example, your roll number was 2413152, whatever. This was your roll number, right? So I can go to this programmer view, and I can actually, oops, for example, your roll number was this, and I can actually see that this number can be seen in hexadecimal format. Over here you can see 170921E. It can be seen in decimal like this. It can be seen in octal representation. It can also be seen in binary representation. These are just representations. Value doesn't change, right? So even if the memory, by the way, it is conventional to write memory addresses in hexadecimal format. This is just a convention, but the value can be represented in hexadecimal, in binary, in octal, in decimal. So normally we are tuned to seeing numbers in terms of decimal format, but you can use hexadecimal representation or octal or binary, whatever you like, right? So programmers tend to use all of these: hex, octal, binary, decimal. Actually, more in hex, octal, binary than decimal. But when you're working on a low level with numbers, by the way, not everyday programmer uses this. So I hope this answers the question, right? Typecasting is slightly different from changing the representation. It is changing the type. Yeah. The type is going to, because the answer may not be very intuitive, but it is more of a design method as compared to intuition, sorry. The thing is that typecasting, it changes the size of variable. So for example, a variable was only occupying this space, like 348, and here it was written 000. But for some reason your function call requires that your number should have like be in 6 digits instead of 3 digits. So now you are using typecasting to increase its size, so that it can fit into or it can fulfill the requirements of that function. So it is different from that, but I can also try and show you the representation thing. If I am not wrong, what we did was, so what the x format specifier does, it changes the representation of this number x from decimal to hexadecimal. And similarly lx changes, it doesn't really it changes the long integer decimal format representation to long hexadecimal representation, right? So if you wanted to see your address, and by the way, I think I skipped this part, that when we are doing this, you can see the value of x is this. And actually let me keep it to decimal, because we have input it in decimal, 45,700. So here you can see this is our number value. So I was telling you about using this picture, that each variable has a value part and an address part. So for variable x, you can see over here that the value part is 45,700. It is displayed over here using memory reading technique, not using the other we did not directly write over here 45,700. That is what I'm trying to say. So the second part is that we received or gained access to or read the value of address of, sorry, the address of, not, I shouldn't be using the word value. We read the address of variable x in memory, and we displayed that address in hexadecimal format using lx. So if you want to display the address in decimal, you can use ld, and you can see the address in memory in by the way, why is it so long? Because if it was a 32-bit system, the address would be just somewhere around this long. But now this is because 64-bit system, the addresses are really long, and actually they can go even further up to this point, but that would be absurd to have such a long address. So they have kept it to somewhere around 48 bits. We will see in the course later, inshallah, that what Intel architecture is using right now in number of bits for different address sizes in the memory chapter number 8. So let's okay, so the most important part in understanding all of this was that you understand that the variable has two parts. One is the value part and one is the address part, and on top of that the compiler provides us the facility to name this address thing, or this address to some readable format. So this is what the compiler does for us. It creates a name that is readable for us. It can have some meaning, and it's easier to remember, right? So this is only the compiler part, not the OS or running part. That doesn't deal with names. It converts it to addresses and plays with the addresses only. So okay, so now let's okay, yeah, now I'm going to define a new variable. I'm going to call it int star p, and I'm going to say that I have declared a pointer of type int, or maybe I should restate this. I have declared a pointer that points to the data of type int. Okay, now I'm going to actually make this pointer point to that data. So let me do that. So I'm going to write p equals ampersand x, right? And now I am going to, do both of these things using, by the way, let me take this over here. Yes. So I'm going to repeat the exact same thing, but without using x. Why and how? Because I have associated the pointer p with x. So what I've done over here is I have forced, or I have made the pointer point to I have made the pointer point to the address of variable x, right? Now let me type the add yeah. So I was saying that I need to eliminate the variable x from this part, and I want to introduce the pointer p over here. And without using a variable name of variable x, I want to display the value of variable x using pointer p. So let me do that. So I will be writing star p over here, and let's see what happens. And similarly, if I may, I will simply write p over here. And let's first of all, let's see the output, and then comment on it. So here you can see that both the lines have exactly the same outputs, right? This is the value of x, this is the address of x. But in the next two lines, I have never used the variable x. You can see there is no x over here, but still I'm getting the value of x and the address of x. How is that possible? It is possible because I made the variable, the pointer p, point to the address of x by writing an ampersand sign in front of, just like I told you over here, that the ampersand sign is the address of operator. It points to the address of a variable. So I have took the address of variable x and I have transferred that address inside the variable p. And then here I have gone to the value of x using the value of pointer p. This is called dereferencing operator, or you can say star operator, I don't know, asterisk operator or whatever. So this is the dereferencing operator, which we have actually dereferenced the value which was referenced to by pointer p, right? So star does that for us. And similarly, here you can see that we are simply, so p was storing the address of variable x, and it is simply printed.